So now let's look at Charles' law. And the first thing I'd like you to notice is the graph. Okay, it's not curved this time. It's basically a straight line that just goes up. Why is that? Well, notice that our equation's a little bit different. This time, basically, we have V1 over T1, or V over T, equals a constant. So it's not the product that equals the constant. It's actually the division that equals the constant. So let's make our little table to kind of see how that works. So let's pick a V and a T, and then we'll do V over T. So let's say the V is 40, and the T is 4. So 40 divided by 4 is 10. That means however these things change, the fraction has to be equal to 10. That's what the relationship is about. All right, well, let's suppose the volume's 20. Then what does the temperature have to be so that it's back to 10? 2. Let's make the volume 80. What does the temperature have to be back to 10? 8. 80 divided by 8 would be 10. Well, notice what's happening in this case. If I go down, the other one goes down too. If I go up, the other one goes up too. In fact, they either go down or they go up by the same proportion. In other words, cut in half, cut in half. Double, double. It's the opposite of what the other one did, what Boyle's law did. And in fact, this is called a direct relationship. They both have to get bigger or smaller the same way. Inverse, they do opposite things. Direct, they do the same thing. However, little wrinkle. Kind of annoying, but it's the way it is. Note right here. It says K for Kelvin. This law only works if you're in Kelvin. Well, what is Kelvin? Basically, Kelvin equals Celsius plus 273. Now, Celsius, we can go negative. Okay? We can have below 0 for Celsius. We can have below 0 for Fahrenheit. There is no below 0 for Kelvin. Kelvin is called the absolute temperature scale. It's always positive. If you got down to 0, basically you're talking about no heat, no energy, no motion at all. Even the electron would be frozen in space if you really had 0 degrees. So we got to make this little switch in order to do this law. So let's look at our first problem. We have a balloon. It's at 27 degrees Celsius. 4 liters of volume in the balloon. Okay, then we're going to heat it up to 54 degrees. Now know what I'm doing here. 27 up to 54. I'm doubling my temperature. Okay, so let's see what happens to the new volume. Will it be double? First thing though, that first temperature, can't use the 27. Have to add 273 to it, which gives us 300 K. And the second temperature, have to take the 54, add 273, and we're up to 327 K. Now notice that in Kelvin, we're not doubling anymore. We're going to go from 300 to 327. So it's going to go up a little bit, okay, but it's not double, not in Kelvin. All right, now we're going to do our problem. Write down the equation. V1 over T1 equals V2 over T2. Put in our numbers. Okay, V1, 4 liters. over T1, 300K equals V2. We don't know the new volume, so put V2 over 327K. Now, this one's a fraction. How do we solve this to find V2? We're going to multiply by the fact that that 327 was down there. So we're going to multiply both sides by the 327K. So over here, it's 327 divided by 327. They'll cancel. And over here, we have 327 times 4 divided by 300. And we end up with our new volume is 4.36 liters. So please note, even though I, quote, doubled the temperature, I did not double my volume. Now you might think to yourself, well, wait a minute, isn't that what the rule should say? But again, only when we're in Kelvin. So doubling it in Celsius doesn't do you any good. Now, let's look at problem 2. Okay, here's my 327. Need to add 273 to it. Turns out that's 600K. My 27, add 273 to it. That's 300K. Note, by the way, that when I have the K's, okay, there's no little circle by them, the degree symbol. It is for Celsius and it is for Fahrenheit, but you don't put it in when it's Kelvin. All right, so here's my T1, and there's my T2, and then here's my V1. And sometimes it's helpful to just label things before you start plugging them in. So, again, write down my equation. V1 over T1 is V2 over T2. Plug them in. 6.8 liters over 600K equals V2 over 300K. Just like I did in problem 1, we're going to multiply both sides by 300K to get that V2 all by itself, because those will cancel. And over here I have 300 over 600. Basically it's just divide by 2, because the 3 and the 6 will cancel. And so I got 6.8 divided by 2. My new volume is 3.4. So what's the big difference between 1 and 2? In problem 1, what I doubled was the Celsius. I didn't end up with double the volume. But in problem 2, note, 600 was double 300. 6.8 is double 3.4. So when it's in Kelvin, the rule works. When it's just in Celsius, the rule doesn't work. Really important. This equation and every other one that has T in it, you have to change the temperature to Kelvin to be able to use the equation. Now you may have to change it back into Celsius at the end of the problem, depending on what the problem's asking for. But you have to always change it by adding that 273. All right, let's try one more, because hey, Celsius, I can go below 0. So here I have a negative temperature. Doesn't change anything. My T1 will be negative 33 plus 273, which is 240K. My T2 will be 87 plus 273, which is 360K. And right there, my 8 liters, there's my V1. Okay? V1, T1, V2, T2. Let's go ahead and plug our numbers in. 8 liters over 240K equals don't know over 360K. Multiply both sides by the 360K. Cancel out over here. 360 times 8 divided by 240, you should come out with 12. Now, you're not going to do that in your head. I don't want you really to be doing that on paper and pencil. Use the calculator, let it do it for you. Again, all I did was go 360 times 8 divided by 240, and there's my 12. That's what you should be doing. But I want you to notice one more thing. 240 went to 360. Basically, 240 times 1.5 is 360. 8 times 1.5 was 12. Whatever the Kelvin does, the volume has to do. Whatever the volume does, the Kelvin has to do. All right, we're going to finish this up with a similar kind of problem to what we just did on the other paper. We're going to do it twice, essentially. Once in Celsius, see what happens, and once in Kelvin, see what happens there. So, no numbers again. Make them up. Volume of a gas is squeezed to half its original volume. All right, so let's make V1, hey, I'll make it 8 again. But now V2 is going to be 4. Squeezed to half. All right, now, what temperature? I don't know, I don't have a temperature, so let's make it easy. I'm going to say my T1 was, say, 400 K. Okay? Round number, 400 K. So, we need to find this one, T2. We have 3 of the 4 numbers. Set it up. V1 over T1 equals V2 over T2. Plug in my numbers. 8 liters over 400 K equals 4 liters over T2. Now, you might think, all right, how am I supposed to solve this? Because the part I don't know, the unknown's on the bottom. Okay? If I divide both sides by this 4, I'm going to have 1 over T, not T. How do we solve a problem like this? We cross multiply. Okay? Go that way and go this way. So 8 liters times the T2 has to equal the 400 K times the 4 liters. Notice what I did. That's what's called cross multiply. 400 times the 4, that got put on this side. 8 times the T got put on that side. But see, now I can solve it. Now, hey, I want T, T2. Divide by 8 liters there. Divide by 8 liters there. So what's my T2 going to be? Well, what's 4 over 8? Half. What's half of 400? 200 K. Now, if the problem had been, how does the Kelvin temperature change? We could say, hey, when I make the volume go in half, the temperature went in half. But it doesn't want to know Kelvin, it wants to know what the Celsius did. Well, what are the Celsius? Well, let's back up a little bit here. 400 minus 273. Well, that's 127 Celsius. 200 minus 273. Well, that's Minus 73 Celsius. Now, if I'd have picked different numbers, they would have ended up in different things. What you'll find is there's no real pattern. All you can say is, hey, when V went down, T went down. That's all I can say. I cannot say like I could on the other problem, go, oh, cut in half, double. It's not going to be anything like that. Not when I'm in Celsius. I can't make anything more than, hey, if the one goes down, the other went down. That's all I can say. If the one goes up, the other goes up. But I can't really tell you how much, because if I'd have picked 500K or 600K, the amount of change would have been different because of that little 273 factor. But here's how I got back to Celsius to check. 127 down to negative 73. All right, let's finish off the last one, 5. How does the Kelvin change if we double? All right, V1 is 8 again. Double, V2 is 16. T1, hey, pick 400K. Come on, we're just keeping it easy. So just like before, V1 over T1, V2 over T2. So 8 liters over 400K equals 16 liters over my unknown. Cross multiply. So I'm going to get 8 liters times the T2 equals 400K times the 16 liters. Divide both sides by the 8 liters to get the T2 all by itself. I got 16 over 8, which is 2, which means the new temperature, it was at 400, it's now at 800. And it's in Kelvin. So in this case, temperature doubled. And no matter what temperature I would have picked, if I'd have picked 300, it would have gone to 600. If I'd have picked 100, it would have gone to 200. It would always double if it's in Kelvin. So the law works in Kelvin. As you can see in problem 4, it doesn't work in Celsius. Any questions?